Refrigerators are quite clever contraptions. In this video, we'll walk through and see how one works. So, first off, let's begin by looking at the compressor. What do compressors do? Well, if you want to really know, there's a compressor right over there, and what they are doing, in essence, is you plug them in. There's actually a plug. You can see the cord right here, so you plug that into a wall socket. You plug it into a wall, and what it's really doing is taking refrigerator gas, refrigerant, and it's pushing it up and squeezing it so it's all compacted. So it's pressurizing that gas. High pressure. Well, guess what? If that is high pressure, then the gas molecules there are bumping faster or bumping harder and bumping more frequently against the walls because it's squeezed up, right? And it's getting hotter, so it's high temperature or higher temperature by the time it comes out on this side of the compressor. So we're going to put high pressure, high temp, gas on this side of the compressor. So when it's coming out of the compressor, it's a gas. Actually, going into the compressor, it's got to be a gas, because if it's not a gas and we try to compress it, well, have you ever tried to compress a liquid? I mean, it'll drip out if it can, but if you just had an enclosed container and you tried to push on it, like with this piston, it would not compress. In fact, it would break your compressor. So, we've got a compressor. I'm just going to label this here, compressor. Okay, so we've got that right there. Now, what happens is, okay, we squeeze the gas, and then what it does is it goes through what we call the condenser. Now, I'm drawing it as these loops right here. And why do we call this the condenser? We call it that because the gas inside is condensing. What do I mean? It's got these gas molecules, and we're allowing the heat to flow out. So if heat flows out of a gas, what happens? We're taking energy out. It starts dripping down to the bottom of these pipes, and it gradually becomes, by the time it comes out, it's all water, or I should say liquid. So it comes out, it's liquid on this side, it's still high pressure, and it's still high temperature. But now it's a liquid. Okay. So you may be wondering, oh, often we indicate Q as heat flowing out. Now you may be wondering, well, wait a minute. We took all this heat out, but it's still at a high temperature. How can that be? What's happened is that energy flowed out because we took it out of the molecules and allowed them to change phase to become a liquid. If they're a liquid, well, they're still hot. It's just that now it's a liquid instead of a gas. So you still have the same high temperature on both sides, both before and after it goes through the condenser. It's just on this side, it's a gas. We lose a lot of energy through heat. And this side comes out as liquid. Okay, so we've got liquid on this side. What does it do? Oh, I should say we want to look and see what the condenser looks like on my actual refrigerator right here. Well, it's coming out, and you can see a little bit by way of tubing on this side. You see that? and then it runs along the top, and you can see where it comes out on this side, and you see these tubes going along, and that is all part of the condenser. And if you look closely, there's insulation right here. So what's happening is the condenser is losing heat to the outside. It conducts through all of that metal that is normally there, and it just allows the heat to flow outside rather than back into the refrigerator. This aluminum foil helps reflect that the infrared radiation portion of that energy or heat that's falling out. So this part right here is all part of the condenser, and this again is the compressor. Okay. So now what happens? It goes through what we call the throttling valve. So I'll label that as throttling valve. Okay, where's the throttling valve? Well, it comes out here, and you can't see it that well. It's a little bit dark, but the throttling valve is this right here. And you'll see it more closely when I walk you through my kitchen, so you'll see the actual throttling valve in real life. Okay, so goes through the throttling valve. Now, if you want to, what you can do is you can think of a throttling valve as kind of like the nozzle on a hose. Look at it this way. If you have a hose and you've got water flowing through the hose, you know it's high pressure on one side of the nozzle of the hose. So the water's flowing down towards this high pressure area, or it is high pressure all on one side of the hose. And as soon as it comes out to open air, it's at low pressure. So this might be at like 70 psi. I don't know, that's pretty high, and then this side is just going to be at your regular atmospheric 14.7 psi, something like that. So your hose drops the pressure. This blockage of the sort of the throttling valve, which is the nozzle, creates a high pressure on one side and a low pressure on another. This throttling valve is doing precisely that. I'm going to draw it for you in a slightly different way. Let's get this out of the way here. Okay, now you can also think of it like this. We have a little valve. We can dial this valve so it goes further and further in, right, and blocking more and more, almost all, of the refrigerant that's flowing through this. And so if we dialed it all the way in, it would block the whole pipe. If we dial it back out, then it doesn't block very much. So this throttling valve, what it does is it takes that liquid that's flowing through it and allows it to drop in pressure. So it will come out the other side as low pressure and low temperature. Okay, so we've got our throttling valve. So it's really cold now. And what happens is we send it right around the area where we want to cool it off. This is called the evaporator. Evaporator. Okay, so that's this area. Let's circle each one of these little rascals. And the evaporator is this right up here. Look, you can see the little coils in my refrigerator. And see how it comes in from the back? Actually, you can't see it here, but it goes into the back and into this part of the fridge right in here. So it's coming out and going inside the fridge. And here you see it coming into here. That might be it going out. We can't quite tell. But it traces along these little tubes that are embedded within this this sheet, and those are the evaporator coils. So what happens there? These are really cold because remember it came out at low pressure, low temperature. So heat falls in. Okay, heat falls in. It's really cold. So heat is now falling into this really cold coil right here, evaporator coil. What's that doing? It's ferrying heat out of this region, which is the region we want to be super cold. And it's actually keeping the rest of our refrigerator cold while we're at it. And so then remember, what does an evaporator do? The heat is going in, so it's taking that liquid and evaporating it, allowing it to become a gas. And it's a darn good thing, as I mentioned later on again, that it becomes a gas, because if it doesn't, then when we try to squeeze it, it would not squeeze very easily. Now, one other thing to note, right off in the corner here, you see this device where you can vary the temperature within the fridge. That's probably connected right in here with the throttling valve. So when you vary that dial right there, what you're doing is varying the amount of blockage you've got in this piping right here. The bigger the drop, the bigger the obstruction you have right here, the bigger the pressure drop, and the bigger the pressure drop, that means the bigger the temperature drop. So in other words, you can make it colder by blocking more. Of course, you reach the point where you block it all, your refrigerator will stop working. But if you obstruct it quite substantially, you can just make it really, really cold, which is precisely what you want. So I had said before, it's gas going in, and I just want to remind you that it's low pressure and low temperature. Right on this side, what's happening? Low pressure, low temperature going into the evaporator takes in a lot of heat. But where is that heat going? Not to raise the temperature, but simply to change the phase. As a molecule, here's the liquid molecules, and remember, one of them will leap the bonds, right, of the surface of the refrigerant and become a gas, and then another one does, and another one does. And as each one does that, they're taking energy off of that liquid and putting it in, that's what causes it to go into gas form. So it takes a lot of heat going in, energy going in, to convert that liquid all into a gas. That's where that heat is going. So it is not going to change the temperature. It is only going to change the phase of the refrigerant. So let's take a last look at how we can parse all of this. Remember the four key components, which are the compressor, the condenser, the throttling valve, and the evaporator. Now, everything above this line, this whole part is high pressure, high temperature, whether it is before the condenser or after the condenser. This whole part right here is low pressure, low temperature, whether it is before the evaporator or after the evaporator. And then if we change, we can say, look at this side. It's always gas before and after it goes through the compressor. On the other hand, it's always liquid before and after it goes through the throttling valve. So there you have it, the key components of the refrigerator. Now let's go to my kitchen and see how it works. Here we are in our kitchen. This is my refrigerator that I'm going to show you, but this is not the refrigerator we normally use. Our normal refrigerator is behind my trusty cameraman and this one, as you can see, is something I've taken apart to show you exactly what's going on with a refrigerator. First of all, there's 4 major components, as you know. The first one is the compressor, and this is the compressor right here. What the compressor does, it squeezes the refrigerant, makes it high pressure, high temperature. Then that goes off here, and this wire itself, you can see how the wire kind of goes through. It's a tube actually, and that's a heat exchanger tube, which is the condenser actually. So this condenser wraps around the refrigerator, and you can see how it's going along the top here, and see how it goes along, and then it comes around, and now it's threading back and forth on the outside here. And you can hear our cat, who is actually focusing on all of this just as well. Okay, so you can see this is all condenser. So it's just this piping that's going here, and the heat can fall out of the condenser, and that's its whole purpose. So notice how there's some very thick insulation here. Maybe you want to come around and take a look at, see how this thick insulation is here. And also, notice how we've got this aluminum foil-like substance right here, and that helps reflect the infrared radiation. So it reflects the infrared radiation, and then so this tube keeps going back and forth. And see how it comes back through here? This is the throttling valve. So this is where it goes from high temperature, high pressure. But remember, because we've given off all of this energy here, then all this heat, the gas that has come out of the compressor is now liquid. So liquid goes through the throttling valve, comes out as still a liquid, but now it's low pressure and low temperature. So that's really cold. And what that does is it goes back through, up in through here. So remember, now it's really cold, like super cold. So we go back inside my refrigerator, and look at there's little coils in here. It is so cold in here that the heat that's inside this container falls into this really cool container right here. These cool coils. These cool coils are the evaporator. What they do, it's almost a little counterintuitive, when the heat falls in, it causes the refrigerant to evaporate by the time it gets through. So it evaporates, comes out, and it's a darn good thing it evaporates, because by the time it comes back into the compressor here from the evaporator, it's a gas. So the gas is able to compress that, or the compressor is able to compress the gas, because if it was still liquid and it tried to compress the liquids are kind of incompressible, and it would be a real problem. So we go back, and it just continues right on with the cycle over and over again. Basically, what we're doing is we're taking heat out of this area. It's open. We're taking heat out of here, and we're using the work from the compressor to pump it up to a high pressure and high temperature, and then throw that heat out into the room. And remember, what runs all of this? Well, you can't see it very well because I've kind of demolished things, but the plug into the socket is what powers all of this, where we're making energy run the wrong way. We're making heat flow out of cold and up into hot, and that's all powered by this electrical compressor. Okay, we're back. So what I want to do now is show you, look, we've got heat. Well, essentially, see, there's heat in this compartment right here, the freezer compartment. And you may think, it's really cold in there. But that's only because we've taken the heat, or we always continue to take the heat from this freezer compartment and allow it to flow into something that's even colder, which are these evaporator coils. And we take that heat then, dump it into something colder, cleverly bump it up using external work from our power source, right, our power plug. We carefully bump it up to high pressure, high temperature, and then we throw that heat outside into the room. So we're taking heat. It's almost like taking a bucket of water. We lift it, carry it up the hill, and then dump it at the top of the hill. That's what we're doing. That's what pumps do, and that's precisely what compressors are doing in this case. So we're very, very cleverly setting things up so heat falls into something a little bit colder, and then we heat it up and allow it to fall outside. So that's why refrigerators are often called heat pumps. Heat pumps. Let's go look a little more closely at this whole idea of heat pumps. Okay, now if we wanted to, we can take a cold area. We're going to call this the cold reservoir. Cold reservoir. And that's going to be at some temperature TC. That means cold temperature, right? What is this? This would be something like right around the freezer compartment or the coils that are in the freezer compartment. Okay. So now, what is the purpose of what we're doing with our refrigerator? Well, what we want to do is we want to take energy out of the freezer compartment and dump it outside, right? And outside is what we call the hot reservoir. Or that's going to be at TH. So what we'll do is we're going to take a little heat, and we're going to call that minus QC. The C stands for cold. The minus sign means it's coming out. We're going to take that heat, and with the application of a little more energy, work, that is, we're going to take both of those. Remember, each one of these is in joules. They're units of energy. We're going to add those both together, and that is going to give us the energy we would dump in our hot reservoir, which we're going to call QH. That's the energy we're dumping in our hot reservoir. This is what a heat pump does. So what we're doing is we're kind of standing back, looking at our whole refrigeration unit, because it's all embedded in this thing, and saying we're taking some heat out of our cold place and we're dumping it in the hot place, and it takes a little bit more work to do that. So look at this, and let's go back and look at this rather busy diagram right here. We can think of this right here is the cold reservoir. Oops. Hope you can see that cold reservoir. Okay, so we've got heat flowing out of the cold reservoir, and then we're dumping it on this side into the hot reservoir. So this whole mechanism right here, all of that is embedded in this right here. So I'm going to put that whole mechanism is symbolized by this process right here, and it's simplified and symbolized. Now later you're going to see that engines go like this. Engines take heat out of a hot reservoir, right? So it'll be minus QH coming out. And then what they do is they swipe some of that heat as work. That's what engines do. Take heat, produce work. And then they throw a little bit away right here as QC, and so that's like coming out of the muffler of your engine or your car. And so engines work exactly the opposite of heat pumps, but we're going to see that later, so we'll make this magically disappear. Now, it turns out, if we go back to our heat pump right here, there is an equation that we can see, and it is this QH is always equal to this plus this, right? They're both flowing in here and combining to form QH. So we can say QH is equal to minus QC, right? There's minus QC plus W. Well, that makes sense. Now, there's one other equation, though. A very, very intelligent man by the name of Sadi Carnot started thinking about, now, what is the relationship between the temperatures here and all of these different quantities? And we won't go into how he discovered what he discovered, but we will talk about the results of what he discovered. And that is that there's a relationship between those temperatures, the work, and the heat that we take out. So these two guys, Q minus QC and W, are related through this equation. And what this equation shows is that if you have the absolutely most efficient heat pump you could ever get, that the best you can do as far as if you put this amount of work in, how much QC could you haul out of that freezer compartment is given by this ratio right here. So let's work a little bit of an example. Let's say that we have a TC. We're going to set TC as, let's make it 250 degrees Kelvin. Okay, and so that's pretty cold. It's like a really cold freezer. Okay, now let's make TH be 350 degrees Kelvin. So that's pretty hot. It's like warmer than room temperature, that's for sure. But let's say that we're trying to pull some heat out of here and stick it in this hot reservoir. So let's see what we've got. If we take 100 joules of work that we put into our compressor, then at those particular temperatures, so we've got 250 over, well, 350 minus 250 is just going to be 100. I set this up so cleverly, so I could do it easily. Okay, so we've got that. Now look, the hundreds cancel, and we've got that minus QC is equal to 250 joules. Now, if that's the case, we can plug this in right up here, and we can say 250 joules plus, well, we set the work is equal to 100 joules, and the amount of energy we can throw here into the hot reservoir is 350 joules. Sounds pretty good. What happens, though, if we take this TC and we make it even colder? Let's say we made it 150 Kelvin. TC, and we'll call that TC prime, is 150. So basically we're working to pull heat out of a much colder freezer area. Okay, we're going to try plugging things into this same equation. So we're going to, we'll call this one we had the first one, and this is the second one, so we'll call it double dagger, right? And double dagger, we're going to have the same work is 100, and then now we've got T cold is going to be 150, and then TH minus TC is going to be 200 instead of 100. And so we end up having, let's see, basically this is 150 divided by 2, so it's 75 joules in this case for minus QC. Whoa, what's going on here? Look, before we had 250 joules for this same work that we're putting in. Now we only have 75. So what this really means is the colder this freezer compartment gets, the bigger the temperature difference between hot and cold, the less energy I can take out of this reservoir right here. And also look, let's see, if we take that 75 and we plug it in here, we'll get, okay, we're going to get minus QC is 75. See, we're replicating what was done in this equation right here. 75 plus W is 100. So we've now only got 175 joules of QH that we're able to throw out into the warmer reservoir. So what this tells us is, look, you can take out a lot more heat of this cold compartment when there's not a big temperature difference between the cold and hot reservoirs than you can if the temperature difference is very large. In other words, if the temperature difference is large, these heat pumps are not very efficient. But there's one last little idea I want to impart to you before I go, and that is that we know this is the freezer compartment, and this was more or less the outside room, right? But there's another way we could use a heat pump. We could actually use a heat pump if we wanted to warm a house. If we situate everything properly, look, this could be like the outside here, this freezer area, and this could be like the inside of your house. So if you want to warm up your house, you can take the energy from the outside, warm it up a little bit by compressing, and then throw it away into your house. So you can use heat pumps to heat your home. This is a great idea if the temperature differences aren't that big. This is why heat pumps are frequently used in southern states. But if the temperature difference is large, for example, in Michigan, these are not going to be very efficient when it's really cold outside, so they don't work very well. And that's all for refrigerators and heat pumps.